what are our products here for, rather, what are the functional groups on our products here? We got these ones, well, first of all, this would be what? Ketone, and this one would be aldehyde. All right, and what is our product going to be if we use these BH4, aluminum H4? These are what we call these hydrides. Okay? And so these are reducing agents, so we get the opposite of our oxidation reactions here. So our products would be not creating more carbon-oxygen bonds, but decreasing the number of carbon-oxygen bonds. So we always get alcohols with these reduction reactions. Okay? So all I really do to get my product is erase one of those bonds, stick a hydrogen on there, right? That's sort of the strategy. It's not like it moves position or anything crazy like that, just the reverse of these oxidation reactions that we learned. So then this one here, same idea, draw my carbon backbone, and then turn that carbonyl group into an alcohol group. Okay? So then when we're talking about naming these compounds, we gotta, as we said, this one's a ketone, and this one's an aldehyde, which is important because we do have different nomenclature schemes for these different functional groups. Okay? Ketones end in O-N-E, whereas aldehydes end in A-L. So for this one, I have 1, 2, 3, 4 carbons. So that's bute. If I go ahead and number here, this would be 2 butanone. Okay, and then actually for this, I would totally accept this. This is perfectly fine. But actually the true proper name for this is just butanone without the 2. Why would that be? Because there's no 3 butanone, right? If I pick this up and move it here, it's still 2 butanone. And remember, that's really the logic behind when we get to drop that locant, that number, is if there's like unambiguous. If it's a 2 butanone, carbonyl group can't be over here, otherwise it's an aldehyde. And if I just moved it over to this carbon, that would become carbon 2. All right, so I would really accept either, but you know, IUPAC rules wise, this would be considered just butanone here. All right, so then this one's an aldehyde. My parent chain are these 1, 2, 3 carbons. And remember with aldehydes, that carbonyl carbon, since it's necessarily on the end in an aldehyde, that's always carbon 1. So that means this is carbon 2, so this would be 2-methyl. And then we don't include the location because again, it's always at carbon 2. So this is propanal. Always just takes a trillion tries, but we're good here. All right. So, the last reaction we're going to learn about this week is what's called a Wittig reaction. Apparently my pen's not connected either. All right. This is the aldehydes and ketones chapter, so we're going to take an aldehyde or ketone. And we're going to react it with what's called a Wittig reagent. Okay? And so the signature of a Wittig reagent, if we just zoom in here real quick, is this PPH3 attached to a double bond. All right? So what the heck is PPH3? So first of all, pH represents what's called a phenyl group, which is a benzene ring. Benzene, if you sort of didn't notice, we kind of glossed over nomenclature of benzene compounds, and that's because they're kind of a huge pain in the butt. When benzene's the parent chain, you call it benzene. When it's a substituent, you call it a phenyl group. Anyways, we're not going to go into that, but that's what that pH stands for. And then the other P would be what? What element? Just phosphorus. So this is phosphorus with 3 gigantic benzene rings coming off of it here. All right, and that's not something that's really going to influence how we do our products, but just FYI. All right. So these reactions here, what we're going to do is we're going to create a new carbon-carbon bond between the carbon at the base of our carbonyl group, our carbonyl carbon, all right, and the carbon at the other end of this Wittig reagent here. The thing that's fairly unique about this is that we actually retain our double bond in our product. So let me just draw out our product real quick. Okay, so take a second to copy that down, and then we'll walk through sort of how we got this here. Okay, so first of all, just sort of keeping track of carbons. These 1, 2, 3, 4 carbons from my aldehyde, or from my ketone actually, are these 1, 2, 3, 4 carbons here. Okay. These 2 carbons come from my Wittig reagent here. All right, so how did I get my products? I'm going to just kind of redraw these substrates here. I'm going to take this and rotate it just to kind of more look like how it is oriented in our product. All right, so notice that how we get our products. I'm going to get rid of this oxygen. I'm going to get rid of this PPH3 business. And I'm just going to pick this up, set it right there. All right, again, I have this oxygen. It's going to be replaced by this new carbon-carbon bond. I just pick this up and set it right there, right? I'm not actually breaking that double bond in either one of these here. I'm just sort of replacing this carbon-oxygen double bond with a carbon-carbon double bond. All right, so let's just practice predicting our products here. I'm going to put down a few more. right, so for this first one, again, if I'm going to predict my products here, I'm just going to start by drawing my aldehyde. So boom, boom, boom. And I'm even going to draw that double bond. I'm just not going to put the oxygen on there, right? Because in this, our new bond is a carbon-carbon double bond. So if these are my 1, 2, 3, 4 carbons from my aldehyde, I'm forming a new bond between my carbonyl carbon and my double bonded carbon on my Wittig reagent here. All right, so when I draw that double bond, now on the other side is that blue carbon, and I just have to include a total of 1, 2, 3 carbons on that fragment as well. So there's 1, 2, 3. Okay. Same thing over here, right? So I'm going to draw my 6 carbons from my cyclohexanone. Put in that double bond, but now I have this new double bond between my carbonyl carbon, and on the other side will be that double bonded carbon from my Wittig. So then I just need to include a total of 1, 2, 3, 4 carbons on this fragment. Make sure they're all spaced out sort of the way they should be here. So I got a branch, and again, I can always double check. 1, 2, 3, 4. What's up?
So again, it doesn't matter which way they're facing, as long as it has those carbons, is it going to be right?
Correct, right? So as long as you connect it, oh, that is a good point here. So because we have a double bond, you would actually get a different, your product would be different if it was up here, okay? So let's just think real quick about these two products here. And we do know reactions that are sort of stereospecific, but let's just draw these two options here again. All right, so here was one option. Well, this is a bad example, actually. This is a bad example because this one's actually perfectly symmetric. So if you picked it up and flipped it upside down, this actually doesn't have any sort of cis or trans or anything like that because it's symmetric. But let's go back to our other one. This one's a better example. So in this case, it literally would not matter. But this one here, let's take a look. So here's this cis product here. I'm sorry, that's the trans product. And then this would be the cis product. Okay? One of these is actually more stable than the other one. All right? Which one, does anybody have a guess on which one that would be, left or right? Trans or cis? So let's just see, no wrong answers, all right? Just to feel it out here. Who thinks that the trans product would be more stable? And who thinks that the cis product would be more stable? All right, why do we think the trans product might be more stable?
It has
Okay, this is really just kind of that argument that we've used a few times before called steric hindrance. When you put two big groups on the same side, they're just much more clashing that can go on. Right? So remember that this bond here can also rotate about. So in your cis conformation, you sort of have collisions between this end of the molecule and this end of the molecule, right? Whereas in your trans structures, those are necessarily located sort of on opposite sides. So the trans structures will form, if there's no sort of stereospecificity in the reaction itself, your trans structure is going to be the more stable, the major product, just because there's that less steric hindrance in the formation of the trans product. Okay, so this would be our major, and this would be our minor product here because of steric hindrance. Oops. Hindrance. Okay. All right. And I guess just to sort of hammer something home real quick, we did learn about these reactions called Gilman reactions from the previous chapter. So let's just see if we can't refresh our memory here. CuLi. What would the product be here? All right, so for these reactions are what were called stereospecific, meaning that you only get one specific stereochemistry out of it, and that is we have to attach our new group from our Gilman in the same way that it was oriented in our reactant, right? So this is necessarily going to give us that cis product. There's no choice because this type of reaction was considered a stereospecific reaction. All right, for our Wittig reagents, these are not stereospecific. So the more stable, i.e. the trans product, will be the major product. You will always get a mixture, but that more stable product, the one that will form due to less steric hindrance, is going to be your major product. All right, and truthfully, Wittig reactions are a little bit more complicated than that, but that's the extent that we're gonna sort of cover them here, okay? We're going to just blanket say that they're not stereospecific, and so that more stable product, which again is the trans product because of steric hindrance. What's up?
When you were on the first demonstration right here, when you were like moving, you were just like putting on top of for the react, like the final product, is there going to be a total of 4 bonds, or is it actually just 2? Like, does it actually get rid of that second bond on the right hand side with PBH?
Yes, so you sort of, I guess when I was picking it up and moving it, really I should have been a little good. It's like you kind of this bond and this bond. So you don't have 4 new bonds forming, you're forming a new double bond though. So this double bond is breaking and this double bond is breaking and you're reforming one new double bond. Okay? Visually it looks like you're just picking that thing up and setting it down on top of that. Okay, but yes. Yeah, one new carbon-carbon double bond is formed. Okay. So let's just do one more here. All right, so again, I'm going to start with my redrawing my aldehyde, my 1, 2, 3, 4, 5 carbons. I'm going to draw that double bond in. All right, but now my new bond is between what used to be that carbonyl carbon, which is the site of a lot of our reactions, right? And my new bond will be the carbon at the base of that PPH3 of my Wittig. All right, I got to put on these 1, 2, 3 carbons here. So I could do it like this, 1, 2, 3. Or I could do it like this, 1, 2, 3. And again, we're going to have our trans product be our major product. So we're not having those carbons clashing up against one another. So this is my Wittig reaction here. Okay, so let's create a little bit of a cheat sheet of these reactions that we should know for aldehydes and ketones here. We're going to make one of those wheel things, all right? So we're going to put just kind of a simple aldehyde in the center here. All right, a good way to study this chapter is to just draw any old aldehyde or ketone and put it in the center and make sure that you can draw the products of all these reactions. All right. All right, so let's fill in this wheel here. Okay, you got 5 structures that you would give me to complete our reaction wheel here. All right, so let's start with the one that's still on the board behind me here. The sodium borohydride. What is my new functional group going to be? An alcohol, right? So I'm going to reduce this carbonyl group. Same number of carbons, oxygen's in the same place, but now it's not a carbon-oxygen double bond, but a carbon-oxygen single bond. All right, if I go over here to my, what do I hit with DMP in order to get an aldehyde? What functional group? That alcohol, that same alcohol, right? If I was being sort of more condensed, I could have just put this over here. Because remember, these are inverse of one another. The one is an oxidation reaction that creates more carbon-oxygen double bonds. The other one's a reduction reaction, which breaks carbon-oxygen bonds, right? So those two are just inverse of one another. All right, so let's go over to this one here. When you see chromium, you think oxidation. Yes, chromium. Anytime we see chromium, it's always doing the same thing, and that is these oxidation reactions. Right? So this is one reagent. The other one, the one that was on our other exam, was the sodium dichromate. But again, anytime you see chromium, you're always thinking the same thing. This is going to be a strong oxidizer. And aldehydes can oxidize to what? What functional group? Can I oxidize this any further, or is it stuck here? Right, it's on the end, so just like a primary alcohol, I could oxidize it fully all the way to what we call a carboxylic acid. So just like primary alcohols, when they're hit with one of these chromium reagents, one of these strong oxidizers, they form carboxylic acids. Aldehydes are the same thing. They can be oxidized further to carboxylic acids. All right, MgBr, our Grignard reagent, one that we've sort of beat to death here. We're going to be creating a new bond between our carbonyl carbon and the carbon at the base of our magnesium here. So I'm going to start by drawing those in. This is my orange carbon here. I'm going to draw a new bond. That means that this is my blue carbon. Then I just have to include that other carbon from my Grignard. And then what am I missing? The alcohol group, right? In a Grignard reaction, my carbonyl is converted to an alcohol group when we create that new carbon-carbon bond. All right, and lastly, the one that we just learned about, these Wittig reactions here. I'm again going to create a new carbon-carbon bond, but this is actually a carbon-carbon double bond. So what I'm going to do is I'm going to draw my carbon backbone. I'm going to draw in my double bond, but now on the other end is no longer that oxygen, but my carbon from my Wittig reagent. Okay, so this is a summary of our aldehydes and ketones. We do have two sort of interchangeable reagents. So for my oxidation, I can have that chromium 6 oxide or the sodium dichromate. And for my reduction, I could also have used lithium aluminum hydride, and I would get the same product, right? So those are interchangeable reagents. They do the exact same thing. There's no sort of special consideration that we have about one doing one thing to something. You know, we can lump them together in our brain as being the exact same. Okay, So then to just focus on these Grignard reactions for one last example here, because again, we've talked about them a lot, so they're ones that we should know pretty well here. If I give you an alcohol, I want you to tell me how you could create this alcohol using a Grignard reaction. So what could you use as your aldehyde or ketone? And what could you use as your Grignard reagent in order to create that new alcohol here? So there's actually two possible answers for this one. So let's look at our alcohol here that we've created. I told you I created this using a Grignard reaction, and we're trying to piece together what those two components would be. There's only one thing that you know for absolute certain here, right? And that is that this carbon here, we know this has to have been the carbonyl carbon. That's the only possibility if this was created using a Grignard reaction, right? Now, what we don't know is which was the new bond that was created, because we have two choices. This could be our new bond. All right, so that means that this fragment over here was my aldehyde. Draw it in the same direction, whatever. Okay, and thus the other fragment was my Grignard. Or the new bond can be on the other side. So again, that's my carbonyl carbon. But this could be my new bond here, which would make this my aldehyde. And my Grignard would be the other part. These 1, 2, 3 carbons here. Okay, but either one of these could be used to create that same alcohol. And some reactions we learn about like, oh, there's a preference for this half being the bigger half or something like that. That's not the case with the Grignards. The Grignards are incredibly flexible. Either one of these reactions would work perfectly well to form that alcohol. Okay? Cool. So we got one more set of reactions to learn from this chapter, what are called aldol addition reactions. And we're going to save that for next week because kind of like our Grignards, we create some ugly products there. So we want to sort of be able to take our time and go over them a few times. So we'll save that for next week. I will make sure that that nomenclature quiz is posted this afternoon after my last class so you guys have the full weekend to work on it.